So in this segment, we're going to talk about or introduce talking about a certain way of thinking about probabilities. It's a way of thinking that many people don't find tempting, but is correct. So it's important to learn to do it this way. So I'm going to introduce this by asking you to imagine the following kind of case. Let's suppose this is you on the right of the screen wearing kind of the greenish shirt, and it's a medical doctor on the left. And the medical doctor, you're in the office because you're getting just a regular checkup, and the doctor says, I want to test you for a virus. And you say, like, look, I feel fine. Why are you testing me? And the doctor says, I'm not worried that you feel fine. I'm just testing all of my patients. And you say, okay, why not? Have at it. So the doctor comes and draws a little bit of blood. You, of course, don't like that. But you say, look, the doctor says, look, we're going to have your results in a few minutes. You say, okay. The doctor exits, comes back a few minutes later with the results and tells you, look, it's positive. You're like, what? I feel fine. And the doctor says, well, you tested positive for the virus. And then you naturally say, well, does that mean I definitely have it? And the doctor says, not necessarily. The test is only 90% accurate. And you say, so there's a 90% chance I have the virus? And the doctor says, sorry. Okay, so that's the kind of case I want you to imagine. And now, if you were lucky, here's what would happen. A statistician would come in, and the statistician would say, hold on, how prevalent is this virus anyway? And the doctor says, well, around 1% of people in the population have it. And the statistician says, well, given that you've sort of been testing people randomly, not based on symptoms, if 1% of the people in the population have it, and the test is 90% accurate, then there's only an 8% chance that a given person who tests positive has it. So there's an only 8% chance you have it, she says to Green. Well, both Green and the doctor are confused. They wonder, how can it be that the test is 90% accurate and I test positive, and yet there's only an 8% chance that I'm infected? And the statistician then explains and says, I want you to think about it this way. How many people did you test? She says to the doctor, and the doctor says 1,000. So she says, and 1% of people have the virus? And the doctor says, yeah, that's right. So then she says, well, approximately how many of the people you tested would you expect to have the virus? And the doctor says, well, 1% of 1,000 is 10, so 10 people. And the statistician says, right. Now, of those 10 who are infected, how many do you expect to test positive? So there's 10 who are actually infected. We know that just based on the base rate, based on the fact that 1% of people have it, and you tested 1,000. So how many of those 10 who actually have it do you expect to test positive? And she says, well, 9. And he says 9, and the statistician says, why? And the doctor says, because the test is 90% accurate, and 90% of 10 is 9. And the statistician says, well, good, let's write that down. So up here we have 10 people who actually have it. So this is 10 people, the P stands for actually positive, 10 people who are actually positive. And we're going to say 90% accurate for the test. So the test is going to, of those 9 people who are actually positive, it's going to test, of those 10 people who are actually positive, it's going to test 9 of them positive. It's going to say 9 have it. And now the statistician says, now how many people who don't have the virus are going to test positive? And the doctor's like, what do you mean? And the statistician says, well, look, the test is only 90% accurate. So some uninfected people, some people who don't have the virus, are going to test positive. How many? And the doctor says, well, since only 10 of the 1,000 are infected, that means 990 of the 1,000 aren't infected. And the statistician says, well, how many of those 990 are going to test positive? And the statistician says, well, since the test is 90% accurate, it's going to get 10% of them wrong. And that means 10% of those 990 are going to test positive even though they don't have it, and 10% of 990 is 99. And the statistician says, good, so 99 people approximately who don't have the virus are going to test positive. And the statistician says, I guess so. Or sorry, the doctor says, I guess so. So then the statistician says, well, let's write that down too. So up here we have 990 who are actually negative. 10% inaccuracy for the test is going to give us 99 of those people who are actually negative testing positive anyway. And the statistician then says, so how many total positive tests are we going to get? And the doctor says 108. And the statistician says, why 108? And the doctor says, well, 9 of the 10 who were infected test positive, so we got 9 positive tests from the positive people, and 99 of the 990 who aren't infected tested positive, so we got 99 positive tests from the uninfected people. So 9 from the infected people, 99 from the uninfected people makes a total of 108. And the statistician says, that's exactly right. And how many of those 108 actually have the virus? And the doctor says, well, only 9. So the statistician says, exactly right. So what are the odds you're infected given that you test positive? And the doctor says, I guess it's 9 out of 108. And the statistician says, which is? And the doctor says, about 8%. And the statistician says, let's write that down too. So we have 9 people here who are actually positive, testing positive, and there's 99 who aren't positive, testing positive. So we get 108 total positive tests. 9 of those are actually positive. So the odds that you're positive given your test are 9 out of 108, which is 8%. So the statistician says exactly. Now, we'll go through further examples next time, but I want you to rewatch this video and think about it, really come to understand what's going on here, kind of understand the procedure that you just went through to solve this problem. It's very similar, the mistake that the doctor and the patient were making when they thought that there was a 90% chance that the patient was infected. The mistake is very much like the base rate mistake that we looked at in the last segment, where we talked about the lawyer and the engineer, and we had a neutral description, and people are inclined to say 50-50 because they let the descriptive information dominate their decision-making, and they ignore the background base rate, the background frequency, the background statistical information, which is that 30% of the population were engineers and 70% were lawyers. So given a neutral description, you'd want to say, well, there's a 30% chance the person's an engineer and a 70% chance the person is a lawyer. Well, it's the same kind of thing. The accuracy of the test is kind of like the descriptive information. We want to let it dominate our decision making. And the background frequency, the prevalence in the population of 1% is the base rate. It's that background frequency. It's the kind of mere statistical information from our point of view that we tend to ignore. But you need to combine, just as in the lawyer engineer case, you need to combine the descriptive information, which happens to be neutral in that case, with the background frequency, which points to lawyer being more probable. Here you have to combine the descriptive information, the accuracy of the test, with the background frequency, which is the base rate in the population, the prevalence of the virus, which is 1%. And the kind of reasoning we just went through gives you a way to do that combination. So we're going to stop this segment there, and we'll continue next time with another example.